All right. This is Unit 7, Lecture 2. We're going to apply the fundamental theorem of calculus. We're going to start by talking about differential equations. You've already solved differential equations. Differential equation is just some derivative set equal to something, as well as perhaps some initial conditions. So an equation with a derivative. Possibly and usually other initial conditions. You'll be asked to solve differential equations, but the solution is not like a value. The solution is an equation. The original function that satisfies all the conditions. It's contagious. Okay. So we want to find f of 4. We're given f of 1 is 3 and f prime of x is equal to 4x plus 2. I can go ahead and find f of x by taking the antiderivative of 4x plus 2, understanding that there is a c. I would use f of 1 is equal to 3 to find that c. Then I would be able to plug in 4 to find f of 4. Let's go ahead and do that for practice, taking antiderivatives, finding c, and going from there. Yes, thank you. Thank you. I really appreciate that. Okay, now this f of x is what we call a general solution. And then once we find c, we find what is called the particular solution. F of 1, which equals 3, equals 2 plus 2 plus c. C is going to have to equal -1. So now that I have f of x, which is equal to 2x squared plus 2x minus 1, this is my particular solution. I can use that to find f of 4. 4 squared is 16 times 2 is 32. 2 times 4 is 8. Minus 1, I get 39. Okay? Piece of cake, right? We've done this before. All right. Well, then let's go ahead and attempt to do this. Let's find f of 6, given f of 1 is 5, and f prime of x is x squared e to the x. What's the problem? No problems? We're good? What do you think, Mr. Wright? What's the problem? Yeah. Don't know how to take the antiderivative of that. You don't know how to take the antiderivative of x squared e to the x. So we're kind of just stuck. Okay, well, let's just pause on that question. Let's come back to it. Let's talk about finding areas between a curve and an x-axis with a calculator. Let's talk about finding the area from 0 to, I don't know, 2 under x squared e to the x. I know I can't take the antiderivative of this, so I can't use the fundamental theorem of calculus, but a calculator has the capabilities of doing lots of calculations really, really quickly. And what it does is a right-Riemann sum, that kind of sum, but with a lot of skinny rectangles. And it uses a right-Riemann sum to approximate this exact area. Now, how we're going to do this is we're going to go to math, and then we'll go down to 9, which is FNINT. So in your calculator, go to math, go all the way down to 9, and you should see FNINT. Okay, now if you have an older operating system, that will pop up. If you have a newer operating system, you see an integral pop up. Does anybody have an old operating system where the FNINT pops up? You do, Miss Willie. You will then type in the following. Everybody else, you can just type in what the integral says and press equals and find out what that area is. Miss Willie, you will do FNINT of the function. So in this case, you're going to do x squared e to the x. You will then press comma. There's a comma next to the parentheses. You'll say, take this derivative with respect to x. Press comma again, and then you'll give it the boundaries starting at 0, comma, going to 2. Okay? So just in general, it's FNINT of the function, comma x, comma a, comma b. Okay, everybody else? Piece of cake, 0 to 2 of x squared e to the x. Dx. And I get, oh gosh, 20.778. Did I? Frustrating. I thought that x went there. 12.778. Okay, cool. Well, can we use that and our calculator's computational capabilities to help us figure this out? The answer is yes. Okay, and it's because of the fundamental theorem of calculus. They seem impossible to solve if you don't know how to find the antiderivative of an equation. Fundamental theorem of calculus, just to remind you, is if we want to find the area from a to b under some function, I'm going to use f prime of x, it's just equal to the change in my antiderivative, correct? Cool. Well, let's say I know how to find this using a calculator, no matter what. But I'm trying to find something like this. All I have to do is add f of a of both sides. No, I'm gonna switch that up. We will find f of a that we don't know. Nope, sorry, sticking with f of b. So I add f of a to both sides, and I get that f of b, some unknown value, is just equal to some known value plus the area under its derivative. We know that this integral is just the change in my function from a to b. So if I have a known and add the change between the known and unknown, I'll find the unknown. Okay? So can we use this to help? For sure. Let's say I have a calculator handy, and I have this derivative, and I don't know how to take the antiderivative, but I'm asked to find f of 6. Well, here is my unknown f of b. Here's my known f of a. Here is f prime. If I want to find f of 6, I just need to take f of 1 and add the change in f between 1 and 6, which is the same as the area under f prime. If I have a calculator, I could do this. Go ahead and tell me what f of 6 is. All we need to do is 5 plus this, but instead of from 0 to 2, we go from 1 to 6. And I get 10,491.435, but it's correct. So this must be like 10,386. $486, yeah. So f of 6 is 10,491. Okay? Awesome. This equation, this application of the fundamental theorem of calculus is used very, very frequently on an AP test, especially when you have calculators handy, or they just kind of test you on your knowledge of this on multiple choice questions where they just give you limited information. Okay, super, super important, and it really does tie together the whole area under something is the change in its antiderivative. Area under f prime is the change in f. We can use the change in f to help us find new values, unknown values of f, if I know a known value of f. Okay? So, we could have done the first example, which gave us that f of 4 was 39. Go ahead and confirm that f of 4 is 39 using this applied fundamental theorem of calculus, where we have an unknown, f of 4 is equal to a known, f of 1, plus the change under f prime. Go. Well, the unknown is your b. Always. The unknown is always your b. And you should see that f of 4 is 39. Let's make sure we get that in our calculator. 3 would have to go outside of the integral. So do the integral with the 4x plus 2, then add 3. Piece of cake, right? If I had a calculator, boom, I don't have to take the antiderivative. I don't have to do anything. I can just plug some stuff in and go from there. F of 4 is equal to F of 1 plus the area from 1 to 4 under F prime. So F of 4 equals 3 plus the integral from 1 to 4 under 4x plus 2. Now, of course, you could do this either way. But the other one could only do it using your calculator because we don't know how to take the antiderivative of that. All right. We could use this knowledge for particle motion problems. Hi, Randy. How are you? Sorry to bother you. Just seeing if we could get scheduled on the stadium tomorrow. Whenever it's available. 6? Okay. We'll go on there at 6. Thank you. Okay, that's fine. We'll check it out at 5:30. If it's available, we'll get on there. But then if not, 6. Thank you. Bye. Let's say I have a question like this, and I said, this is a calculator question, or this is in the calculator section. Now, in the calculator section, you don't have to use your calculator. Turns out only half of the calculator questions on an AP's calculator section, you'll actually have to use your calculator. The other ones are just random questions that typically you don't do any calculations for. It's like interpretations of graphs, et cetera, et cetera, et cetera. But if you have velocity and you want to find a position at a specific time, well, we know that position, if you took the derivative of position, that gives you velocity. I know that x prime is v. So if I want to find a position at 2 pi over 3, that'll be equal to an initial position, which will be my position at time 0, plus the change, which will be the area under x prime. Well, x prime is the same as v. Okay? Now, you could take the antiderivative of v, you could find the c value, or you could just do this. Okay? So let's just practice plugging that into our calculator really quickly, and we're good. I can't wait till the sun comes out. My goodness, is it dreary. And what do we get? Huh, what an answer. Okay, so we can use this to our advantage. Now, most of the times, there will be one option or the other available to you. Either there is a No calculator question, and you could still do this without your calculator. However, I would prefer to use the find C method to find the antiderivative. That's what I do. But you could do this. It's just a little bit extra work. But there will be certain situations like this one where you definitely don't want to take the antiderivative to figure out C and to go from there. So we're told the velocity is -2 plus t squared plus 3t to the 6/5 minus t cubed. Known that s of 0 is 10. Write an expression involving an integral that gives the position. Use this expression to find the position of the particle at time 5. This is from an AP free response question. If you know this application of the fundamental theorem of calculus, you won't attempt to find this antiderivative. I don't want you to do that. Instead, you just write f of b equals f of a plus the integral from a to b under f prime, but using v and s. Okay? So in this situation, I want to find my position at time 5. You're told that position is s of t, not x of t. Sometimes they do that. Okay, just write that down. That's half of your answer. The other half would be to type this into your calculator correctly and to use 10 here. Now, it's important to know that you could go like back in time. If you want to know your position at time 2, and let's say you're given the position at time 5, well, just make sure you know that this is f of b and this is f of a. Your a would be 5, your b would be 2. Okay? This may happen, and if it does happen, that's okay. So write a little note. Mind your b's and your a's. Okay? So we're comfortable with, straight line motion, derivatives of position or velocity. So areas under velocity is change in position. That's cool. Well, let's talk about rates. We will have a lot of problems where we will be told the rate at which something is growing or blah, 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 is given by R of t, or the growth of something is given by G of t. Okay? Here's an example. Plant receives coal at a rate, G of t equals that equation, tons of coal per hour. If the plant opens the day with 500 tons of coal and accepts coal over an 8-hour period, how many tons will the plant finish with at the end of the day? Okay. It's very important that when you see the word rate or the growth, the rate, you understand that this function that they give you, that's a derivative. Though they give you in terms of like capital G, it is the derivative. It is the derivative of some other function that they didn't give you, like t, where t is the total amount of coal, or just the amount of coal. T prime would be the change in the rate of the amount of coal. T prime in this situation would be G. Okay, they give you it, and they don't use a little tick mark, but since they tell you it's a rate, you think of it, oh, that's the change in a total. Well, here's our situation. I want to figure out how much coal I have at this plant at the end of the day. If you think about T being a total amount, I need to find T at time 8. Okay, go ahead and find T at time 8. There's the ticket right there. It's super simple, but a lot of people have no idea where to start with this problem. Let me get it. 13255. Is that what you got, Ms. Parr? That looked right. Did anybody else get 13255? 1325.55. Is that what you got? 1325.55. Now, here's the important thing. For this to work, you need your function, its derivative. Okay? The area under a derivative is the change in its antiderivative. This is going to give me the change in the total amount of coal. It essentially gives me how much coal is being added by finding the area under the rate at which coal is being entered. If I plugged in a value into G, it is not telling me how much coal has been entered. It's telling me the rate at which it is arriving. That is not great when you want, like, the values are not great. They'll just be positive or negative, means like we're adding more coal, we're adding less coal, we're adding this much coal, we're not adding that much coal, et cetera, et cetera. But man, if I find the area under a rate, all of a sudden I have a total, a change in an overall. Oh, I know. Ready? Boom. There we go. All right. So 1,325 tons of coal. Okay. Water enters the container at a rate W of T, which equals 50 e to the negative 0.5 T gallons per second. The container had 20 gallons at time T equals 0. How much water is in the tank at T equals 10 seconds? Go. Now, to handle these, I do like to come up with a different function that represents the total amount of something. If we're given a rate, that's the derivative of my total. Here, the total, this would be the rate at which it's just entering. T would just be the total amount that is entered. But if I just want the total amount of water at 10 seconds, I can just take the total amount of water at 0 seconds and add the change in water, which will be the area under T prime, which in this case is W. And we get 119 gallons. All right, last problem, and then we're done. I'm giving you the answer. Let's see if we can get this answer on our calculator. Go. Yeah, it's not exactly right there. Not exactly right. That's good. Really look at the details of the question. That's the key. You got it, Mr. Wright. The details of this thing. For 20 to 25, the function w has a derivative that's that. That's important. If you got 74, that's not exactly right. We're used to having 0, but in this case, good. Since this derivative is only defined for 20 through 25, we are going to say the water temperature, and this W, this capital W, is the actual temperature. They're going to really screw with you. Next class, all we're going to do is practice rate problems. And you'll see that all these free response problems with rates. And sometimes a capital letter will be a total, like a temperature. Sometimes the capital letter will be like a derivative of temperature, the rate at which the temperature is changing. Sometimes they won't give you this prime. They were nice in this situation. Because W prime is defined for 20 to 25, we will use W of 20 and go from 20 to 25 under W prime. And that is how we will get 73.043. I like how a lot of people were thinking using 0 and 55, and you got an answer that was really, really close. But we're looking for that answer. Okay? All right, that's all I got. You can start working on your homework. It's a simple lesson today. It's just really one thing, but it's a very, very important thing. And we'll be using it a lot next class and on the AP test.